Last section we discussed orthogonal or perpendicular vectors. Today we are going to apply this idea to entire subspaces of a vector space. Think of this in the same way that you would think of two lines being perpendicular. So we have two perpendicular lines here. Or we can talk about a plane and a line that's perpendicular to it. So it comes down here and intersects it. So I should make that solid. And it's perpendicular to the plane. What we shouldn't think of, though, is having two planes that are perpendicular. So imagine we have here one plane coming down and intersecting another plane. In such a way that we actually do form right angles at that intersection. Sort of like, think of a floor being perpendicular to a wall. The concept that we're going to be working with here is not going to include this third case. It's going to be more similar to these other two. And we'll kind of explain why that will be as we go. It'll kind of contradict some of the results that we are going to get. But we're going to say that if we have two subspaces x and y of Rn, they are going to be orthogonal if anytime we take a vector x from x and y from y, those two vectors are always orthogonal. So in other words, x transpose y equals x for every little x in x and every little y in y. We are going to use that same notation that we used for, so if we just have little x and y being orthogonal, we wrote it like this, saying x perp y. We can also write capital X perp y as a way of saying that these two subspaces are orthogonal to each other. Let's take an example here. So for our first example, we'll work in R3. We're going to take the x-axis and the y-axis. So the x-axis, which we'll call this one x, capital X. This is the set of all points x, 0, 0, where x is a real number. And our y-axis, we'll call it capital Y, is a set of all points 0, y, 0, where y is a real number. So if we take, or I guess these should be column vectors, so we'll put a transpose there. If we take any vector in x, we transpose it, so we'll leave off the transpose now, and we multiply it to any vector in y. This time it will have the transpose there. So this is a vector in x transpose times a vector in y. What we will get is x times 0 plus 0 times y plus 0 times 0. Everything has a 0 in it, so we get a 0 overall. No matter which vectors we picked from x or y, we'll always get 0 over here. That's saying that these two are orthogonal subspaces. They are perpendicular to each other. As another little example, we'll go ahead and keep. Actually, let's look at why this floor and wall example doesn't work. Let's take the xy plane. So here we're still going to call it x. Just to stick with the notation that they have in the definition. This is the points, all the points x, y, 0, for x and y being real numbers. And then we'll have the xz plane. Again, I'm going to call this y. This is all the points x, 0, z. I guess we should make those transposed. And let's look at the scalar product of a vector from x and a vector from y. So we have something like x, y, 0 multiplied to x, 0, y, or sorry, x, 0, z. If we multiply those together, actually, let's go and let's pick particular ones. Instead of saying x, y, and xz, let's go ahead and pick numbers. We'll go ahead and just say 1, 1 for that one, and 1, 1 here, or 1, 1, 0, and 1, 0, 1. If we multiply those two together, we'll get 1 times 1, so we get a 1 here. We get a 1 times 0, so 0, and then 0 times 1 to get another 0, and finally we end up with a 1. These two vectors are not orthogonal to each other. So by this definition, even though we might want to think of them as being perpendicular in a geometrical sense, these two subspaces are not orthogonal. Another useful thing to note about orthogonal subspaces is that if we want to test if two subspaces are orthogonal, we do not have to check every single pair of vectors. Let's say that we have a subspace X, which is the span of vectors x1 through xr, and a subspace Y that is a span of vectors y1 through ys. Usually we probably want to think of these as being bases, but we don't necessarily have to. Just as long as we know that we can span those subspaces using these vectors. Let's assume here that we know that for every x, so let's say an xi, and every y, so yj, that we always have these being perpendicular. They're always orthogonal. In other words, xi transpose yj is 0 for every choice of I and j, every choice of these two vectors from these two spans. That will actually be enough to show that x and y are orthogonal to each other. That's because if we pick any other vector, let's say a little x in x, so x is, say, alpha 1 x1, alpha 2 x2, through alpha r xr, and we take a little y in y, so y is going to be, say, beta 1 x1, beta 2 x2, and here we have beta s xs. Why did I make those x's? Those are supposed to be y's. So this would be a y here, and y here. Sorry about that. If we take the scalar product of these two vectors, we can go ahead and replace the x with its expansion. It's a linear combination of the little x's. Times the expansion of y in terms of the little y's. And then while this is the product of two big sums, we can then go ahead and expand it out. We'll have a lot of terms in here, but we'll have like a term alpha 1, beta 1, x1 transpose. Sorry. Oh, I need to not do that. That's supposed to be a t. So x1 transpose y1. We'll also have a term alpha 1, beta 2, x1 transpose y2. So here the x1 got paired with the y1, and here the x1 got paired with y2. Then we'd add the x1 paired with y3, and so on and so forth. We have a lot of terms here. In fact, r times s terms. But the point here is that we already assumed that no matter what x and y we choose, xi and yj we choose, we will always get 0 for that scalar product. Each one of these is some coefficients in front of a scalar product. So we have a 0 here for this first one, we have a 0 here for this one, and every other term after this point is also going to be 0. So overall, we still get 0 for this entire sum. So it doesn't matter which x and y we choose from these subspaces, their scalar product is going to be 0. And that's what we want to have true for them to be orthogonal. So Essentially, this means that if we have a basis for x and a basis for y, we can just test the basis vectors. We don't have to test every single other vector, and that saves you a ton of work. If we start with a subspace of Rn, it's actually easy to come up with another subspace that is orthogonal to it. We can just take all vectors that are orthogonal to everything in our subspace Y. So here we have a definition. Let Y be any subspace of Rn. The set of all vectors in Rn that are orthogonal to every vector in Y. First of all, we denote it as with this notation, Y with the perpendicular sign. Usually I'll just call that Y perp, just because it's easy to say. Then we have this long expanded form of that. So it's all the x's in Rn where x transpose y is equal to 0 for every single y in capital Y. We're going to call this set the orthogonal complement of y. And the main important thing about that is if y is a subspace, then y perp is also always a subspace of Rn, no matter what. Now, it's not going to be the only space. It's not going to be the only subspace that is orthogonal to Y. There are definitely other ones, or can be other ones, in fact. But it is kind of the biggest one. It's the biggest subspace of Rn that is actually orthogonal to Y. In fact, should say that if X is orthogonal to Y, so X and Y here being subspaces, then X is a subset of Y perp. It's a very useful fact. Proving that Y perp is a subspace of Rn for any y is a relatively straightforward, but I'm gonna leave the proof to the book. I'm not gonna prove everything in this section. There's quite a few proofs. Some of them more involved, some of them relatively straightforward. But I'll just leave it to the book for most of it. I do actually want to mention this other remark that they include. Probably should have had it in before we define the orthogonal complement, but they put it here. If x and y are orthogonal subspaces of Rn, then x intersected with y equals a zero vector. That means if x and y are orthogonal to each other, then the only thing that they can have in common is the zero vector. There can't be any other vector in both of them. This is not too hard to see. If z is in that intersection, then what does that mean? That means that z is in x and z is in y. That's what the intersection means. That means that because if we take something in x and something in y, they have to be orthogonal to each other. That means that z has to be orthogonal to itself. That z transpose z has to be 0. But remember, z transpose z is the square of the magnitude of z. And so that's saying that z has a magnitude of 0. That just means that z has to be the 0 vector. Basically, the only vector that's orthogonal to itself is the 0 vector. And this is kind of an easy way to see why the floor and a wall cannot be orthogonal. They definitely have more than one point in their intersection. They actually have an entire line of points in their intersection. And so they cannot be orthogonal under our definition. We would like to get a lot of examples of spaces that are actually orthogonal to each other. And for that, we are going to go back to talking about matrices. So here we're going to have A being an m by n matrix. We remember that we have subspaces that are associated with A. We have the row space. We have the column space. And we have the null space. And we've only given a notation for one of these. The null space has a notation n of A. in this section, they give us notations for the other two. So we're going to denote the range. So we're calling it the range because that's what the range is in term. If we think of A as a linear transformation, we're going to call that R of A. That's why we use R here. But remember, the range of A is actually the column space of A. Any vector that we can get out by multiplying by an x is going to be a linear combination of the columns of A. So it's in the column space. The row space we can actually get by looking at the transpose. If we transpose the matrix, we turn columns into rows and vice versa. So all the rows become the columns of A transpose. And so we can look at the range of the transpose, and that will just be the span of all the original rows of the matrix A. So we'll say that the row space is R of A transpose. Now, remember the book is being kind of picky about whether or not we refer to the rows of A as being actually row vectors or instead of column vectors, and I'm not making that distinction here. So it's saying here that a vector is in R of A transpose if and only if Y transpose is in the row space of A. I'm just going to refer to R of A transpose as the row space itself, because that's really how you want to think about it anyways. But this gives us very nice ways of actually denoting these spaces without having to write row space and column space every time. I'm not sure why they didn't give us these notations back when they first defined the row and column space, but they will be very useful in this section. We'll be using them a lot. In fact, there are relationships between these two, all these spaces. So the row space, remember R of A transpose, turns out to be the orthogonal complement of it turns out to be the null space. And the orthogonal complement of the column space turns out to be the null space of not A, but of A transpose. So let's go ahead and prove this fact. Let's pick our A here. We'll call it, well, we'll denote it as this thing. So we have all these entries. And we'll say that we have some vector x. Specifically, we want this vector x to be in the null space of A. If we do that, then what is A times x? Well, A times x is supposed to be 0, because x is in the null space of A. But if we actually write this out, remember this 0 is actually the 0 vector. Alright, sorry about that. Let's continue. Where were we? So we have this matrix A. We have our vector x. This is supposed to be in the null space of A. So Ax is going to be 0. Or really, this is supposed to be the 0 vector. But what happens if we just multiply A to x directly? Then it's going to be a column vector. The first column is going to be the first row of A times this column. So you have A11 times x1 all the way through A1n, xn. Then we keep going like that. We have AM1, x1, all added to same thing, all the way to AMN, xn. But what that's saying is that for any one of these rows, so for any row I, say, we have AI1 times x1 through AIN xn has to be 0 because this is supposed to equal the 0 vector. What this is saying is that the product of the scalar product of the row I and x is all the x's, is 0. That means that x is orthogonal to each of the rows. And if x is orthogonal to all the rows of A, then remember, if it's orthogonal to all the basis vectors, or a spanning set of a space, then it's orthogonal to the entire space. Therefore, every single thing in the null space is orthogonal to everything in the row space, and so the null space and the row space, written in this way, sorry, that should be a T, these are orthogonal to each other. Now, that doesn't immediately mean that the null space is the orthogonal complement of the row space. It just means that some of the vectors in the row space are orthogonal to, some of the vectors that are orthogonal to the row space are in the null space. The null space is a subspace of the orthogonal complement. But we need to show that the null space is in fact the entire orthogonal complement. So let's assume that we have a vector that is in the orthogonal complement of the row space. Actually, I'll leave that off there. So we're taking the row space, written as R of A transpose, we're taking its orthogonal complement, and we're saying that x is something that's in there. So if x is perpendicular or orthogonal to the row space, that means that if we write, let's name the rows of A as A1 through AM. So here, these are all row vectors. It'll be a little easier to work with it that way. We want to see what happens if we take A times x. Well, very similar to what we were doing before. If we take A times x, then we do each row of A times the entire column vector x. So in fact, what we get here is A1x through AMX. Now we don't have to put the transposes here because I'm actually using the A's as row vectors. So you can kind of say that we are already doing the transpose part. But we're assuming here that x is orthogonal to the row space. That means it has to be orthogonal to each of the rows. A1x has to be 0. AMX has to be 0. In fact, all of them have to be 0. So we do get the 0 vector. That means that x has to be in the null space of A. So now we've shown that not only is everything in the null space orthogonal to the row space, but in fact everything that is orthogonal to the row space is in the null space. So the null space is in fact the entire orthogonal complement of the row space. Now the other part of the theorem is just saying that the null space of A transpose is the column space, the orthogonal complement of the column space. And really, all this is all you have to do to prove that one is replace the A in our proof before with A transpose. We're just using a different matrix, but we're doing the exact same thing. But this does give us a way to find the orthogonal complement of the column space, just by looking at the null space of the transpose. We'll go ahead and use that fact a little bit later. Now, because I'm running a little bit long, I'm going to go ahead and split this video up into 2 parts. We'll go through some of the other results of this chapter, and actually we'll make use of a lot of this stuff. But I'll see you in the next one.